Hello students, today we are going to start with the first part of electrochemistry, in which we are going to discuss certain basic concepts like oxidation, reduction, methods of balancing chemical equations, electrochemical cell, half cells, electrodes, electrochemical series, types of electrochemical cells, types of batteries, and various other related concepts. Let's start with electrochemistry itself. English scientists John Daniell and Michael Faraday are credited as the founders of this branch of chemistry. We can define electrochemistry, that branch of chemistry which deals with the relationship between electrical energy and chemical energy and the interconversion of one form into another form. Electrochemistry is based on the concept that flow of electricity through a substance may induce a chemical change in the substance. Similarly, a chemical change may cause a flow of electricity through some external circuit. The next term is oxidation. The process which involves addition of oxygen or loss of electrons or increase in the oxidation number of an atomic system can be defined as oxidation. Another process is reduction, which involves gain of hydrogen or gain of electrons or decrease in the oxidation number of an atomic system. We must keep in mind that oxidation and reduction are complementary processes. None of them can take place in an isolated way. They take place side by side. Since oxidation and reduction are complementary processes, that means that if one of the species is getting oxidized, some other species is getting reduced with it. It gives us another term, redox reaction. So redox reaction can be defined as a chemical reaction which involves oxidation and reduction. So let's take the example of copper ions and zinc. In this reaction, copper ions are getting reduced to copper, whereas zinc is getting oxidized to zinc ions. So the oxidation half is the oxidation of zinc into zinc ions, and the reduction half in this reaction is the reduction of copper ions into copper. A redox reaction always involves transfer of electrons from the reducing agent to the oxidizing agent. Now we get two more terms. One is the reducing agent and the other is oxidizing agent. Let's see what are they. So the oxidizing agent can be defined as the species which gets reduced in a reaction, oxidizing the other species. So in this reaction, copper ions are the oxidizing agent because they are oxidizing zinc into zinc ions, and in this process they themselves are getting reduced to copper. Similarly, reducing agent is that species which gets oxidized in a redox reaction, reducing the other species. So in this redox reaction, zinc is the reducing agent since it is reducing copper ions into copper and it itself is getting oxidized into zinc ions. The redox reaction that we just discussed was very simple reaction and perfectly balanced as well. But we must know how to balance a given skeletal redox reaction. One approach is the hit and miss approach, but it can be done in a systematic way as well. So there are two methods for that purpose. First is the oxidation state method and the second is ion electrode method. Let's see what are the various steps involved in these methods. The first method is the oxidation state method proposed by Johnson. In this method, the first step is to write the skeletal equation for the chemical change taking place. Then oxidation numbers to the reactants and the products are assigned. The change in the oxidation state is determined for the oxidation and the reaction half. This change in oxidation numbers is then equalized by multiplying with a suitable coefficient if required. Substances other than hydrogen and oxygen are balanced in the reaction by multiplying with a suitable number if required. Then the oxygen atoms are balanced by adding water molecules to the deficient side. For balancing the hydrogen atoms, in case the chemical reaction is taking place in an acidic medium, hydrogen ions are added to the deficient side. But in case the chemical change is taking place in basic medium, the hydrogen atoms are balanced by adding water molecules to the deficient side and hydroxyl ions to the other side. This method will become more clear to us once we discuss an example. Let's take this example. We have to balance this given equation. So first of all, we'll assign oxidation number to all the elements involved in the reaction. In HNO3, the oxidation number of hydrogen is +1. We already know how to assign the oxidation numbers. That of nitrogen is +5 and that of oxygen is -2. Of iodine is 0. Again, hydrogen is +1. Oxidation number of iodine in HiO3 is +5 and of oxygen is -2. In NO2, the oxidation number of nitrogen is +4 and that of oxygen is -2. In water, oxidation number of hydrogen is +1 and of oxygen is -2. Now first of all, let's consider the oxidation reaction that is taking place. This is the oxidation reaction that is taking place. As we can see, the oxidation number of iodine is increasing. Therefore, this is an oxidation reaction. The oxidation number of iodine in I2 is 0 and of HiO3 is +5. So the change in oxidation state for iodine will be 0 minus 2 into +5. Since there are 2 iodine atoms, this will be equal to 0 minus 10, that is -10. -10 is the change in the oxidation state. Now let's have a look at the reduction. HNO3 is getting converted into NO2. The oxidation number of nitrogen in HNO3 is +5 and that of nitrogen in NO2 is +4. As you can see, the oxidation number of nitrogen is decreasing. Therefore, this is the reduction reaction. So the change in the oxidation state will be +5 minus +4. That is equal to 1. Now for balancing the change in the oxidation state, we are going to multiply the reduction half with 10 and the oxidation half with 1. So we'll get the equation 10 HNO3 plus I2 gives 2 HiO3 plus 10 NO2 plus H2O. Now the elements other than hydrogen and oxygen involved in this reaction are nitrogen and iodine. So first of all, let's check for nitrogen whether the nitrogen atoms are balanced or not. On this side of the arrow, that is the left side, we have got 10 nitrogen atoms, and on the other side as well there are 10 nitrogen atoms. So nitrogen is balanced. Now let's look out for iodine. On the left hand side there are 2 iodine atoms, and on the right hand side also there are 2 iodine atoms. Therefore, iodine is also balanced. Now let's balance the oxygen atoms. 10 into 3, that is 30 oxygen atoms are present on this side, whereas on this side there are 3 into 2, that is 6. 6 plus 10 into 2, that is 20. That gives us 26 plus 1, 27. There are 27 oxygen atoms. So the right hand side is deficient of oxygen atoms. So for that case, we are going to add water molecules to the deficient side, that is the right hand side. So on adding 3 water molecules to the deficient side, we get 2 HiO3 plus 10 NO2 plus H2O. This is the same equation as above. Since this side requires 3 more oxygen atoms, we are going to add 3 more water molecules to it. Or we can write 10 HNO3 plus I2 will give 2 HiO3 plus 10 NO2. On adding these water molecules, we can simply write 4 H2O. So after oxygen atoms, let's check out for hydrogen atoms. This side has 10 hydrogen atoms and this side has 2 plus 4 into 2, that is 8. 8 plus 2, 10. So now this equation is our perfectly balanced chemical equation. That is 10HNO3 plus I2 gives 2HIO3 plus 10NO2 plus 4H2O. The second method is the ion electron method proposed by Jett and Lameu. In this method, the chemical equation is split into two halves, the oxidation half and the reduction half, by putting the appropriate number of electrons involved in the chemical change. Then we balance the atoms other than oxygen and hydrogen in the two halves by multiplying with suitable coefficients if required. Then we balance the oxygen atoms by adding water molecules to the deficient side. For balancing the hydrogen atoms, in case the chemical change is taking place in the acidic medium, we add hydrogen ions to the deficient side. And for basic medium, we add water molecules to the deficient side and hydroxyl ions to the other side. Then the charge in the half reactions are equalized by adding electrons. And ultimately, the two half reactions are added to obtain completely balanced chemical equation. Let's take an example to clarify this method. Now we have to balance this redox reaction using the ion electrode method. So the first step is to split this reaction into two half reactions, one for oxidation and the other for reduction. This is the one half. MnO4 minus gets converted into Mn2 plus, and the other half is Fe2 plus getting converted into Fe3 plus. This is the oxidation half and this is the reduction half. So first of all, we'll balance the oxygen atoms. In this half reaction, there are 4 oxygen atoms given on the left hand side but none on the right hand side. So we are going to add 4 water molecules to the deficient side, that is the right hand side. On adding water molecules, we can write MnO4 minus gives Mn2 plus 4H2O. There are no oxygen atoms in this half reaction, so they are not required any balancing. Now let's count the hydrogen atoms. There are 4 into 2, that is 8 hydrogen atoms present on the right hand side but none on the left hand side. We can see that this reaction is taking place in the acidic medium, therefore we are going to add hydrogen ions to the deficient side, that is the left hand side. So on adding 8 hydrogen ions to the left hand side, this is the equation we get. Again, there are no hydrogen atoms in this half reaction, so they do not require any balancing. The next step is to equalize the charge. The charge on the left hand side is -1 plus 8H plus. That is -1 plus 8. We'll get plus 7. And on this the charge is of course plus 2. So we are going to add 5 electrons to the left hand side to equalize the charge. So the reaction will be MnO4 minus plus 8H plus 5 electrons will give Mn2 plus 4H2O. Now here the charge is plus 2 on left hand side and plus 3 on right hand side. So we are going to add 1 electron to the right hand side. So the equation that we get is Fe2 plus will give Fe3 plus an electron. Now since there are 5 electrons in this half reaction and 1 in that, for equalizing their numbers in both, we are going to multiply this half reaction with the coefficient 5. So we get 5 Fe2 plus, we give 5 Fe3 plus 5 electrons. Now we are going to add the half reactions. On adding the half reactions, first of all let's write the left hand side, which is MnO4 minus plus 8H plus plus 5 electrons plus 5 Fe2 plus. Now let's write the right hand side of both the reactions. It is Mn2 plus plus 4H2O plus 5 Fe3 plus plus 5 electrons. These 5 electrons will get cancelled. Since there are no other common species to be cancelled any further, our final equation will be MnO4 minus plus 8H plus plus 5 Fe2 plus will give Mn2 plus plus 4H2O plus 5 Fe3 plus. This is our final balanced chemical equation. Our next topic is electrochemical cell. We can define electrochemical cell as a device which is capable of drawing electrical energy from a chemical change or facilitating a chemical change by the introduction of electrical energy. An electrochemical cell consists of two half cells. Each half cell consists of an electrode and an electrolyte. One of the electrode is the cathode and the other one is the anode. The half cells may have same or different electrolyte. Sometimes the half cells have the same electrolyte but the concentrations are different. We are going to discuss it in more detail when we discuss the types of electrochemical cell. There are certain rules laid out by IUPAC for representing an electrochemical cell. According to those rules, first of all, the half cell which represents the anode, that is that electrode at which the oxidation takes place, is written. Then the electrolyte of the anode is mentioned along with its concentration. A pipe is used between the electrode and the electrolyte, denoting that the two are in different phases and hence there is a surface barrier. If the two electrodes, that is the anode and the cathode, are separated by a salt bridge, we use double pipes to denote that salt bridge after the anode. Then the cathodic half cell is represented. First of all, we write the electrolyte of the cathode half cell along with its concentration. Then we use a pipe and then we write the cathode of the cathode half cell. In case a gas is used in the electrodes, we represent the anode before the gas and the cathode after the gas. Pipe is used to separate the electrolyte from the gas. For example, in case of platinum electrode, for anode we are going to write platinum, which represents the anode, H2, that is the gas, and then H plus after the pipe, which represents the electrolyte containing hydrogen ions. This representation is meant for anode. In case of cathode, we are going to write the gas, then the electrolyte, and then the cathode. So, as we discussed, we represent the anode before the gas and the cathode after the gas. Let's take an example. We have to represent an electrochemical cell as per the IUPAC rules, which consists of a copper cathode dipped in unimolar solution of copper sulfate and a zinc anode dipped in a unimolar solution of zinc sulfate. The two electrodes are separated by a salt bridge. So as per the IUPAC rules, first of all we are going to mention the anode, which is the zinc anode. S represents the solid state. We are going to use a pipe character to separate it from the electrolyte, which is zinc sulfate. We'll mention its concentration, which is given to us, 1 mole. This anode is separated from the cathode by using a salt bridge, which is indicated by a double pipe. Then first of all, the electrolyte of the cathode is mentioned, which is copper sulfate. Its concentration is given to us, that is 1 mole. Then we use a pipe character again to separate it from the cathode, that is copper, which is again solid. This is the representation of the electrochemical cell as per the IUPAC rules. Cell reaction. As we just discussed, an electrochemical cell consists of two half cells. One of the half cell consists of the anode at which the oxidation takes place, and the other half cell consists of the other electrode, that is the cathode, at which reduction takes place. When these reactions of the half cells are combined, we obtain the cell reaction. We just represented a cell in the previous example, which is actually the representation of a Daniell cell. So in a Daniell cell, at the anode, that is the electrode at which the oxidation takes place, zinc is oxidized into zinc ions, and at the cathode, copper ions are reduced to copper. When these two half reactions are added, we get the overall cell reaction, that is zinc plus copper ions will give zinc ions plus copper. In an electrochemical cell, the electrons flow from the negative electrode, that is the anode, to the positive electrode, that is the cathode, in the external circuit. This flow of current from one electrode to the other indicates that there is a difference between their potentials. So the difference of potential which causes the flow of current from the electrode of higher negative potential to the electrode of lower negative potential is known as the electromotive force, which is also denoted in short as EMF. Electrical energy can be expressed in terms of EMF as well. It is equal to the product of EMF expressed in terms of volts and the quantity of electricity expressed as coulombs. There exists a correlation between the change in free energy and EMF as well. Minus delta G, that is the change in free energy, minus sign indicates that there is a decrease in the free energy, is equal to the product of N, that is the number of electrons transferred in a balanced cell reaction, F, that is Faraday's constant, whose value is 96500 coulombs, and E, that is the electromotive force. When we arrange the elements in order of their standard electrode potentials, we obtain a series which is known as Electrochemical Series. A species which has a low standard reduction potential has a thermodynamic tendency to reduce another species which has higher standard reduction potential. So for the sake of learning, we can say that low reduces high or high oxidizes low. This is the basis of the activity series of metals as well. Let's have a look at the electrochemical series. This is an electrochemical series in which the species are arranged in order of their standard reduction potential. Lithium, which has the lowest reduction potential, or we can say as the highest negative value of reduction potential, is the strongest reducing agent, and fluorine is considered as the strongest oxidizing agent. Let's see what are the conclusions we can derive from the series of these elements and their given values of standard reduction potentials. The species with lower values of standard reduction potential, that is higher negative values, will have greater tendency to get oxidized into positive ions, or we can say that they are good reducing agents. For example, the reduction potential of potassium is equal to minus 2.93 volts, whereas that of sodium is equal to minus 2.71 volts. So among sodium and potassium, potassium will have a higher tendency to oxidize. The next conclusion from the series is that an element with lower reduction potential, that is higher negative value, will replace the element with higher reduction potential from the solution. Thus, potassium ions can replace sodium ions from the solution. So we can write that potassium plus sodium ions will give us potassium ions plus sodium. Then a species with higher standard reduction potential has greater tendency to accept electrons to undergo reduction. These elements with higher reduction potentials have greater oxidizing power. For example, the reduction potential of bromine is equal to 1.09 volts, and that of chlorine is equal to 1.36 volts. So chlorine is stronger oxidizing agent than bromine. The standard electromotive force of a cell is depicted by E0 cell. Its value is equal to the standard electrode potential of the cathode minus the standard electrode potential of the anode. Since in the representation of an electrochemical cell we write cathode on the right side and anode on the left side, we can also say that E0 cell is equal to E0 right minus E0 left, where E0 right is the electrode potential of the right side and E0 left is the standard electrode potential of the left side. Now the potential of the electrodes in contact with its ion in a solution depends on the concentration of the ions. It can be determined with the help of Nernst equation, which was proposed by scientist Walther Nernst. Nernst equation is used to determine the equilibrium reduction potential of a half cell in an electrochemical cell. And thus we can use this equation to determine the EMF of the cell as well. Consider a reaction in which Mn plus ion combines with n electrons to form M. So if E Mn plus M is the reduction potential, E naught Mn plus M is the standard reduction potential, R is the universal gas constant, T is the temperature, N is the number of moles of electrons transferred in the balanced half reaction, F is Faraday constant, then we can write the Nernst equation for this given reaction as E Mn plus M, that is the reduction potential, is equal to the standard reduction potential plus RT divided by NF into natural log of Mn plus, where Mn plus is the concentration of Mn plus ions. In a similar way, for an electrochemical cell whose overall reaction is AA plus BB gives CC plus TT, we can write the Nernst equation as E cell is equal to E naught cell minus 2.303 RT divided by NF into log C raised to C into D raised to D divided by A raised to A into B raised to B. Now we know that the value of R is equal to 8.314 joules per Kelvin per mole. Value of T, if we take as 298 Kelvin, and F, that is the Faraday's constant, as 96500 coulombs. Then on replacing these values in this part of the equation, we get 0.0591 divided by N, where N is the number of electrons transferred in the balanced cell reaction or the electrode reaction or half cell reaction. So we can replace this particular part with 0.0591 divided by N. So now we have seen that we can use Nernst equation for the complete cell as well as the half cell. Let's take the example of an electrochemical cell in which the cell reaction is zinc plus copper ions gives zinc ions plus copper. We can relate the equilibrium constant of this cell reaction denoted by capital K with the standard EMF of the cell, which is denoted by E naught cell. Now at equilibrium, E cell is equal to 0. So if we replace E cell by 0 in Nernst equation, we get 0 is equal to E naught cell minus 2.303 RT divided by NF log concentration of zinc ions divided by concentration of copper ions. On rearranging this equation, that is by taking this part to the left hand side of the equal to sign, we get E naught cell is equal to 2.303 RT divided by NF log concentration of zinc ions divided by concentration of copper ions. Now we know that K, that is the equilibrium constant, is equal to concentration of zinc ions divided by concentration of copper ions. So if you replace this part by K in the rearranged equation, we get E naught cell is equal to 2.303 RT divided by NF log K. Now at 298 K, that is, we replace T by 298. We know the value of R. It is 8.314 joules per Kelvin per mole, and F is equal to 96500 coulombs. If we substitute these values in this part of the equation, we get 0.0591 divided by N. On replacing this value in the equation, we get E naught cell is equal to 0.0591 divided by N into log K. Now we just discussed a formula, that is minus delta G is equal to NFE. I hope you remember this. We can also write it as delta G is equal to minus NFE, or delta G naught is equal to minus NFE naught. If we replace the value of E naught from this equation, we get delta G naught is equal to minus 2.303 RT log K. With the help of the relation delta G naught is equal to minus NFE naught cell, we can determine whether a given cell reaction is spontaneous or not. Now, if E naught cell has a positive value, the overall value will be negative for delta G naught. So the reaction would be spontaneous. But in case the E naught cell value is negative, two negative signs will make a positive and delta G naught will be positive, and the reaction would be non-spontaneous. Now for K, that is the equilibrium constant, if it's greater than 1, that means that E naught is greater than 0, which again indicates a spontaneous reaction. Sometimes the reaction's direction can be reversed by manipulating the concentrations of the product and the reactant species. But we must keep in mind that for any given reaction for which E naught is equal to 0, the reaction will proceed from left to right. We must keep in mind that here we are talking about E and not E naught. Electrode potential is an intensive property. Suppose we know we have two cell reactions, one is reaction A and the other is reaction B, and we know their electrode potentials, which are suppose EA and EB. Suppose there is another reaction C, which is obtained either by adding these two reactions or by subtracting them. We cannot obtain the electrode potential for this cell reaction by simply adding or subtracting the electrode potentials for cell reaction A and B, because electrode potential is an intensive property. But Gibbs free energy is an extensive property. So if we know the free energies for this and this reaction, and we obtain C by adding or subtracting these two, we can obtain free energy change for this reaction as well by either adding or subtracting the values of free energies for these two reactions. And then we can calculate the electrode potential for this reaction by using the relation delta G naught is equal to minus NFE naught, or delta G is equal to minus NFE. Another point to keep in mind is that the electrode potential is independent of how we write the reaction. For example, 2Ag will form 2 silver ions plus 2 electrons, or Ag will give Ag plus electron. For both the reactions, the value of electrode potential is same. But it is not so for change in free energy. Since delta G naught is equal to minus NFE naught, it depends on N, that is the number of electrons involved in the reaction. It is 2 in this case and 1 in this case. So the way change in the free energy will be different for these two reactions. Now let us see what are the various types of cells. The first type are the concentration cells and the second are the electrochemical cells. Concentration cells can be further classified into electrolyte concentration cells and electrode concentration cells. And electrochemical cells are again of two types, the electrolytic cells and the galvanic cells. Let's see what are the differences between these types of cells. The first type of the cells is the concentration cell, in which the electrodes and the electrolytes in both the half cells are of the same type, but they differ in concentrations. The half cell which has the lower concentration of ions is made the anode, and the one which has the higher concentration of ions is made the cathode. The concentration cell derives its potential from the difference in the concentration between the two sides of the cells. This is an example of the concentration cell, in which we can see that the electrodes are both the same, that is of copper. The electrolytes are also the same, but the concentration of the electrolytes is different. On the left hand side, the concentration of copper sulfate is C1, whereas on the right hand side, the concentration is C2. This is a simple representation of the concentration cell. As you can see, both the electrodes are the same, that is made up of copper. The electrolytes in which the electrodes are dipped are also the same, that is copper sulfate solution, but the concentration of the electrolyte solutions are different. The copper which is present in this electrode, that is the anode, oxidizes into copper ion and two electrons are liberated. This copper ion is then released into the solution. Thus, gradually this solution becomes more concentrated. The two electrons which are released then travel to the other side, where they combine with the copper ion from the solution and deposit the copper on the electrode. Thus, this solution gradually becomes diluted. This is the general representation of concentration cell, in which M on both the sides denotes the electrode, M plus is the electrolyte, AQ denotes its aqueous state, Cl is the concentration of the electrolyte in the left half cell, and Cr is the concentration of the electrolyte in the right half cell. As per the Nernst equation, we can write the EMF of the concentration cell as E cell is equal to E naught cell plus RT divided by NF natural log Cr upon Cl. Now, in case of concentration cell, the value of E naught, that is standard potential, is equal to 0. We already know the values of R, T and F in standard conditions. So, on substituting these values in this equation, we get E cell is equal to 0.059 divided by N log Cr upon Cl. In order for the concentration cell to work, E cell must have a positive value. That means the value of log Cr upon Cl should be positive. It will be positive only if Cr is greater than Cl. The concentration cells can be further classified into two types. First is the electrolyte concentration cell and the second is the electrode concentration cell. In electrolyte concentration cell, the electrode compartments are exactly the same except for the concentrations of the electrolytes in which the electrode are dipped. We discussed this example when we were discussing concentration cell. The second type is the electrode concentration cells, in which the electrode themselves have different concentrations. This happens when the electrodes used are of amalgams or are gas electrodes, in which the gases can have different pressures. The second type is the electrochemical cell, which consists of two metal electrodes which are dipped in electrolytic solution. It can further be classified into two types. First is the electrolytic cell and the second is the galvanic cell. We will discuss these two cells one by one. Electrolytic cell. In electrolytic cell, the cell reaction is a non-spontaneous reaction which is carried out by using the electrical energy. The electrons are forced out of the positive electrode, which is the anode, and they move into the cathode, which is the negative electrode. The second type of the electrochemical cell is the galvanic cell, which is also known as voltaic cell. In this type of cell, the cell reaction is a spontaneous reaction, and this chemical energy of the reaction is converted into electrical energy. It consists of two half cells which are separated by using a porous pot or a salt bridge. Each half cell consists of an electrode which is dipped into an electrolytic solution. Of course, the electrodes are of two types. At one electrode, the oxidation takes place, which is known as anode and is positively charged. At the second electrode, reduction takes place. It is called cathode and is negatively charged. In an electrochemical reaction, the cations move towards the cathode and the anions move towards the anode in the electrolyte. But in the external circuit, the electrons move from the anode to the cathode. In a galvanic cell, to avoid any confusion regarding which electrode is negative, which is oxidized, or reduced, which is positive, you can use a small trick. Just remember the acronym LON. L-O-A-N. L stands for left, O stands for oxidation, A stands for anode, and N stands for negative, lone. So that makes left electrode is the one at which oxidation takes place. It is known as anode and is negatively charged. But please remember that this acronym or this trick works only for the galvanic cell and not for other types of cells. Daniell cell is a very good example of a galvanic cell. It consists of two half cells. In the first half cell, in which oxidation takes place, the electrode is made up of zinc, which is dipped in a unimolar solution of zinc sulfate. Since oxidation takes place as this electrode forms the anode. So while representing the anode, we write the electrode first, that is zinc, and S represents its solid, then a pipe character, which means that there is a difference between the phases of these two. Then we write the electrolyte, that is the zinc sulfate, and we mention its concentration as well, which is 1 m. Instead of zinc sulfate, we can also write zinc ions. In the other half cell, reduction takes place, that is, this part forms the cathode. It consists of a copper cathode or copper electrode, which is dipped in unimolar solution of copper sulfate. So in case of cathode, we first write the electrolyte, that is copper sulfate, and then mention its concentration, that is 1 m. Then a pipe character separates it from the electrode, that is copper. As seen earlier, we can also write copper ions instead of copper sulfate. So the representation of Daniell cell will be, first of all, we'll mention the anode, that is zinc and zinc sulfate, that is the electrolyte in this half cell, and then we mention the cathode, that is copper sulfate, the electrolyte, and copper, that is the electrode. These two parts, that is the anode and cathode, are separated by a double pipe character, which means that they are separated by a salt bridge. This is a simple schematic representation of Daniell cell, in which the anode is made up of zinc dipped in zinc sulfate solution, and there is a copper cathode which is dipped in copper sulfate solution. The zinc at the electrode breaks into zinc ion and liberates two electrons, which then travel to the other side, that is the cathode, and combine with the copper ion in the solution to deposit copper on the electrode. Our next topic is the battery. A battery is either a single electrochemical cell or a combination of two or more electrochemical cells, generally connected in series, which are used to convert stored chemical energy into electrical energy. They can be classified into two types, primary battery and secondary battery. Let's see what is the difference between these two types. In a primary battery, once the reactants have been converted into products, no more electricity is produced. The cell reaction is irreversible and the battery becomes dead after the reaction is completed. Primary batteries can be used only once. Zinc carbon batteries and alkaline batteries are primary batteries. Leclanche cell or dry cell is the most common example of primary battery. It consists of a zinc container which acts as the anode, and a graphite rod surrounded by powdered manganese dioxide and carbon black, which acts as the cathode. The space between the anode and the cathode is filled with moist paste of ammonium chloride and zinc chloride. The oxidation occurs at the anode, in which zinc is reduced to zinc ions and the reduction occurs at the cathode. Ammonia produced in the reduction reaction combines with zinc to form a complex whose formula is ZnNH3 plus. The cell has a potential of nearly 1.5 volts, but when the current is drawn from the cell, the voltage drops in it. Since the electrolytic medium is acidic, zinc metal slowly dissolves in it from the container. This is a diagrammatic representation of Leclanche cell or dry cell. This container, which is formed of zinc, acts as the anode, and this carbon rod surrounded by a mixture of manganese dioxide and carbon black acts as the cathode. This space, shown in grey color, fills between the two electrodes, that is this rod and the container, is filled with moist paste of ammonium chloride and zinc chloride. In the external circuit, the current flows from the anode to the cathode. The second type of batteries are the secondary batteries. In a secondary battery, the cell reaction is reversible. So we can reverse the cell reaction by passing electricity through the cell, which we call charging. Thus, we can use the battery number of times by a large number of discharging and charging cycles. A rechargeable cell behaves as a galvanic cell during its functioning and as an electrolytic cell during its recharging. Lead storage cell is the most common example of secondary battery. A lead plate acts as the anode, whereas the cathode is formed of lead oxide and dilute sulfuric acid is the electrolyte. At anode, oxidation takes place and lead sulfate is formed, whereas at cathode, reduction takes place and lead sulfate and water are formed. By combining these two half reactions, we can get the overall cell reaction, which is given as this. Now, when the plates get coated with lead sulfate formed in the cell reaction and the electrolyte gets diluted with water formed during reduction, the cell gets discharged. To recharge the cell, the electrodes are to be forced to flow in the opposite direction, which is done by passing electricity through the battery. The normal car battery that we use every day is a lead acid battery. This is a simple diagrammatic representation of a lead storage cell. This cell is a plastic container filled with dilute sulfuric acid, in which a lead plate acts as the anode and lead dioxide constitutes the cathode. In the external circuit, the current flows from the anode to the cathode. Types of electrodes. The most common types of electrodes used in cells are standard hydrogen electrode, metal-metal ion electrode, amalgam, metal-insoluble salt, salt and ion electrode, gas electrode, and redox electrode. We'll discuss what are the constitution of these electrodes and how are they represented one by one. The first electrode is the standard hydrogen electrode, which is also denoted as SHE in brief. It consists of a platinized foil or a platinum foil itself surrounded by hydrogen gas at pressure equal to 1 bar and the temperature is equal to 298 Kelvin, immersed in a unimolar electrolytic solution of hydrogen ions. We can represent this electrode as PT, which stands for platinum, comma the gas, that is hydrogen. G stands for its gaseous state. 1 bar is its pressure, separated by a pipe character from the electrolyte solution of hydrogen ions whose concentration is 1 mole per liter. This electrode is used as a standard electrode for measuring the standard electrode potentials for other substances. It is assigned an arbitrary value of 0. And the other substances whose electrode potentials are to be measured using SHE as a reference electrode are given values using this 0 volt value as a reference. We can use this electrode as a cathode as well as anode. When it acts as a cathode, reduction takes place in which hydrogen ions are converted into hydrogen gas, and when it acts as an anode, oxidation takes place in which hydrogen gas is converted into hydrogen ions. This is a diagrammatic representation of standard hydrogen electrode, in which there is a platinum electrode surrounded by hydrogen at 1 atmospheric pressure. The temperature is maintained at 298 Kelvin and the electrolytic solution is unimolar solution of hydrochloric acid. The second type of electrode is the metal ion electrode, in which a metal rod or plate is dipped in the solution of its own ions. Its general representation is MS, a pipe character, M plus aqueous, where MS represents the metal in solid state, that is as a rod or plate, and M plus aqueous denotes the electrolytic solution of that metal ion. Its example can be zinc rod or zinc plate dipped in the solution of zinc ion, such as zinc sulfate. The next type of electrodes are the amalgam electrodes, which consist of a metal amalgam rod or plate dipped in the solution of metal ions. Metal amalgam is used instead of metal to improve the activity. This is its general representation, in which M stands for metal, Hg is the mercury, so M-Hg stands for metal amalgam. S denotes the solid state. This pipe character denotes the difference between the phases of the two. M plus is the metal ion and aqueous denotes its solution state. Its example can be zinc amalgam rod dipped in zinc ion solution, such as zinc sulfate solution. The next type of electrode is the metal insoluble salt in ion electrode. As the name itself indicates, it consists of a metal which is in contact with its own salt, whose solubility is negligible, and is also in contact with a salt solution whose anion is same as that of metal salt. This is its general representation, in which M denotes the metal, Mx is the insoluble salt, and X minus is the salt solution, in which the anion is same as that in the metal salt. In the first example, we can see that the metal is silver. Silver chloride is the insoluble salt of silver. Actually, its solubility is pretty low. It's not 100% insoluble. And then the potassium chloride solution is there. As we can see, the chloride anion in potassium chloride is same as the anion in the metal salt of silver. Another electrode, which is also known as calomel electrode, consists of mercury as the metal and mercurous chloride as the metal insoluble salt and potassium chloride solution as the salt anion solution. The next type of electrode is the gas electrode, which consists of an inert metal dipped in such a solution which can give the ions of a gas. So we can represent it as Ms, which denotes the metal separated by a pipe character from X2, which is a gas, and X plus or X minus are the ions of the gas, which are present in the solution state. So in the first example, platinum is the inert metal which is dipped in a hydrogen ion solution. Hydrogen ions are the ions of hydrogen gas. Similarly, platinum dipped in chloride ion solutions is also a gas electrode, in which chloride ions are the ions of chlorine gas. The next type of electrode is the redox electrode, which consists of an inert metal dipped in a solution of two salts of a metal such that the two salts have the same metal but in different oxidation states. This is the general representation, in which Ms represents the metal in solid state, that is the inert metal, and M plus X aqueous and M plus Y aqueous denote the two salts which are of the same metal, of course, but in different oxidation states. For example, platinum, which is an inert metal, can be dipped in solution of salts of iron such that iron is in +2 state in one salt and +3 state in the second salt. Our next topic is the fuel cells. Fuel cells are those electrical cells that are discharged to convert the energy from the combustion of fuels directly into the electrical energy. In the most simple fuel cell of its kind, hydrogen and oxygen combine to form water. The reaction takes place in the alkaline medium, that is in presence of NaOH or KOH. So at the anode, oxidation takes place in which hydrogen is converted into water. At the cathode, reduction takes place in which oxygen forms hydroxyl ions. The overall reaction is obtained by combining these two reactions, in which hydrogen combines with oxygen to form water. This is a simple diagrammatic representation of fuel cell. Hydrogen enters from this inlet. This is the anode. Oxidation of hydrogen takes place into water here. This is the cathode and oxygen enters from this route. Oxygen is reduced into hydroxyl ions. The water that is formed and the heat that is evolved exits from this outlet. In the external circuit, the current flows from the anode to the cathode. The thermodynamic efficiency of the fuel cell, which is denoted by neta, can be given as delta G upon delta H, where delta G is the change in free energy and delta H is the change in enthalpy. We have already discussed that delta G is equal to minus NFE, where N is the number of electrons transferred in the cell reaction, F is the Faraday's constant, and E is the electrode potential. So we can also write neta as minus NFE upon delta H. Now let's solve a few questions based on the concepts that we have just discussed. We have to find the expression for the EMF of the given half cells. The first example given to us is this. I hope you remember that for a given cell reaction represented as AABB gives C plus small d into capital D, we had written that the EMF will be E naught cell, that is the standard potential, minus 0.0591 divided by N log capital C raised to small c, capital D raised to small d, upon capital A raised to small a, capital B raised to small b. For this half cell, we can write the half cell reaction as H plus electron will convert into half H2. This is the gas whose pressure is given to us 1 atmosphere. Now this is a reduction reaction. So the EMF of this half cell will be E H plus slash half H2 is equal to E naught H plus slash half H2 minus 0.0591 upon 1. Since the number of electrons exchanged in this half cell reaction is 1, log H2 raised to 1 by 2 divided by H plus. Now if you remember standard hydrogen electrode, this was the representation of SHE, and we also discussed that it has been given a arbitrary value of electrode potential equal to 0. So E naught H plus slash half H2 will be 0 minus 0.0591 log 1 upon H plus. That is the concentration of hydrogen ions. The pressure is also always given to us, that is 1 atmosphere. So we have substituted the value 1 here, and this total part comes out to be 1. Now we can rewrite this particular equation as 0.0591 log H plus. This is the expression for the EMF for the given half cell. Here is another half cell given to us. The cell reaction for this half cell will be Pb2 plus 2 electrons will give Pb. So as per Nernst equation, the EMF of this half cell will be EPb2 plus slash Pb is equal to E naught Pb2 plus slash Pb minus 0.0591 divided by N. Since the number of electrons exchanged in this reaction is 2, we'll write 2 log Pb upon Pb2 plus. Now we can find out this value from any table or electrochemical series that we discussed. Its value is minus 0.13 volt. So minus 0.13 minus 0.0591 upon 2 log 1 upon Pb2 plus, since Pb is solid. This can be written as minus 0.13 plus 0.0591 divided by 2 log Pb2 plus. This is the expression for the given half cell. This is the third half cell. Again, just like the previous two examples, we are first going to write the half cell reaction, which is Cu2 plus 2 electrons will give Cu. The Nernst equation for this half cell will be Cu2 plus slash Cu is equal to E naught Cu2 plus slash Cu minus 0.0591 divided by N, which is 2 in this case, log concentration of Cu divided by concentration of Cu2 plus. This value is 0.34, which is always the same, minus 0.0591 by 2 log 1 upon Cu2 plus, or we can write it as 0.34 plus 0.0591 divided by 2 log the concentration of Cu2 plus. This is the EMF for the given half cell. The next question is, can copper ion oxidize silver to silver ion? Now we know that oxidizing agent itself gets reduced while oxidizing the other reactant in a redox reaction. So we can put the question as, can silver reduce copper ions? Now what we can do is we can write down the oxidation and reduction reactions involved, then calculate electrode cell potential from the half cell electrode potentials. So the reactions in this case will be 2Ag, which will convert into 2Ag plus 2 electrons. Now the standard electrode potential, which we can see from any standard electrode potentials table, is equal to minus 0.8 volt. So delta G0 in this case will be, we know it's minus NFE. Sorry, NFE naught. We have already discussed it. This will be equal to minus N, that is 2 in this case. F will keep as such, into minus 0.8 volt. This will be equal to 1.6 Faraday. The other reaction will be the reduction of copper ions. So Cu2 plus plus 2 electrons will give us Cu. The standard electrode potential in this case is 0.34 volt, and delta G0 will be minus NFE. So minus 2 into F into plus 0.34 volt. It will come out to be minus 0.68 Faraday. The overall reaction which we can obtain by adding these two reactions will be 2Ag plus Cu2 plus will give 2Ag plus Cu. I hope you can recall that we discussed that delta G0 is an extensive property. So when we are adding two reactions, we can add their delta G0 values as well, but it is not the case with E0 values. So first of all, we have to calculate the delta G0 value for the overall reaction, and then by using this relation we can calculate the E0 value for the overall reaction as well. So now for this overall reaction, delta G0 will be equal to 1.6 F minus 0.68 F, which will be equal to plus 0.92 Faraday. Since delta G0 value is positive, reaction is not spontaneous. We can also find the EMF of the cell and prove that it is negative, so reaction is not feasible. E0 for the overall reaction will be delta G0 divided by minus NF. We have obtained this equation by rearranging this relation. It is equal to 0.92 Faraday divided by minus 2F, which is minus 0.46 V. So the EMF of the cell is negative, so this reaction is not spontaneous. This cannot take place. The next question is, we have to construct a galvanic cell from the given pair and find out the EMF of the cell formed. So first of all, we are going to calculate the electrode potentials of both the half cells and then figure out that which half cell will become anode, that is oxidation will take place in that, and which will become cathode, that is reduction will take place in which half cell. And then we are going to write the expression of that half cell and calculate the EMF. So EMF for the first half cell, that is this one, will be E0 Sn2 plus slash Sn minus 0.0591 divided by 2, since Sn2 plus will require 2 electrons to form Sn, log Sn divided by Sn2 plus. Now this will be equal to minus 0.14. We can find out this value from the table of standard electrode potentials. Minus 0.0591 divided by 2 log 1 upon Sn2 plus concentration. This is equal to minus 0.14 minus, in fact we can write it as plus 0.0591 by 2 if we write it as log Sn2 plus, minus 0.14 plus 0.0591 divided by 2 log, the concentration is given to us, that is 0.1. On solving this part, we'll get minus 0.14 plus 0.29, that is 0.15 volts. The EMF of the other half cell, Ni2 plus slash Ni, will be equal to E0 Ni2 plus slash Ni minus 0.0591 divided by 2 log concentration of nickel divided by the concentration of nickel ions. We have taken N is equal to 2 since it will require 2 electrons for nickel 2 plus to get converted into nickel. On substituting the values, we can write minus 0.25 minus 0.0591 by 2 log 1 upon Ni2 plus, or minus 0.25 minus 0.0591 divided by 2. In fact, we'll write it as plus when we take nickel 2 plus as the numerator instead of denominator. Minus 0.25 plus 0.0591 divided by 2 log, the concentration is given to us, that is the value is 0.1. On solving this part, we'll get minus 0.25 plus 0.29 is equal to 0.04 volt. Now the EMF of the earlier cell that we calculated, that is ESN2 plus slash SN, was equal to 0.15 volt. Since the reduction potential of tin is higher, it will get reduced or form electrode of galvanic cell where reduction takes place, that is the cathode. And the half cell of nickel will form the anode where the oxidation takes place. So we can represent the cell as nickel 2 plus nickel, that is the anode, slash SN2 plus SN solid, that is the cathode. And EMF of the cell will be equal to EMF of the half cell at the right hand side minus EMF of the half cell at the left hand side. That will be equal to 0.15 minus 0.04, that is equal to 0.11 volt. This is our answer.